Colloquium. Our speaker today is Dr. Harish Manohara from NASA's Jet Propulsion Laboratory. Harish obtained his bachelor's in instrumentation technology from Bangalore University in India. He got a master's in nuclear engineering from Louisiana State University, and then obtained a PhD in engineering science, also from LSU. After that, he continued in LSU for 3 years as a faculty member before moving over to the Jet Propulsion Lab in the year 2000. Did a number of things in JPL, and since 2005, he's been leading the group on devices over there. He has a number of inventions to his credit, over 20 inventions for which he's won Space Act Awards. He's also won JPL's Lew Allen Award. So let's welcome Harish to the University of Washington, and we look forward to hearing his talk.
Thank you. Am I on? Okay. Thank you very much. It's really a pleasure to be here and give this talk at University of Washington. The only time when I knew of University of Washington is one of my friends used to be here a long time ago in chemical engineering. Other than that, 2 times I was aware of this was when LSU visited Huskies here to play a game. And after that, this is the only time I've come to Seattle, and it's a beautiful city, I got to tell you. So going back to the talk now, the title slide here I wanted to show you because I don't know how many of you have seen JPL. So this is basically the San Gabriel Mountains, and the campus is situated at the foothills of San Gabriel Mountains. Here's the Angeles Crest National Forest. So it's a pretty big campus. We have about 5,000 people or so, and a considerable number of deers and few snakes. And we also have once or twice a couple of mountain lions who visit us, complete disregard for visitor paperwork. They just walk in. So with that in background, it's a pretty interesting place to work. And today my talk will be focused on carbon nanotube applications for space. And it is safe to say that in the research of nanotechnology, especially the carbon nanotube, which started it all, this field emission is by far one of the most researched topics, and perhaps one of the most mature topics as well, that is more close to application than many other topics that are currently being worked upon. Quick acknowledgement, my group and past contributors who were in my group, and my collaborators and multiple funding sources, starting from NASA and the internal R&D, DARPA, Army, and commercial sources. So let me get right to it. Why carbon nanotube? Why do we want carbon nanotube for space exploration? I can give you 3 good reasons, and that's the main motivation for conducting most of the research that is happening today in field emission at JPL. Number 1 is the electronics for extreme environment. Extreme environment actually constitutes an environment harsher than the harsh environments. So I'll show you an example of, in terms of radiation as well as temperature, the temperature extremes that you have to deal with. Secondly, miniature analytical instruments for in situ exploration. So a lot of the robotics mission, when you have a lander, like for example on Mars, we have Mars, and then Curiosity, which is on its way to land sometime around August. You have to have payload or the instruments that do in situ analysis of the science information that you need, in situ measurements, and they have to be conducive for robotic exploration, which is low power, lightweight, and occupying a smaller real estate, etc. So for that, you need miniature analytical instruments, and that's one of the main reasons why you would need carbon nanotube, because the field emission source, it actually starts off or spawns off multiple analytical instrument development activities. And finally, high-frequency sources. These are terahertz sources. So terahertz is a very important spectral region for space exploration, because majority of the emission lines that come from galaxies and interstellar dust is in that region. So a lot of us, in doing remote sensing, they do passive radiometry. They listen to these lines, and they know remotely they can identify the composition of the upper atmosphere, for example, of a distant planet or galaxies. So those are 3 reasons, and I'm going to go over them one by one. Extreme environment. So typically, this is one of the most overused slides. So you're going to see the variation of the environment, operating environment of many components that are put on spacecrafts, and starting with Earth's orbiter. So here is the Earth's orbiter. You have the LEO, that is low Earth orbit, and the GEO, which is geostationary. And the temperature range is not a whole lot. It's from 0 to 50 degrees, something like that in that range. And then the integrated dose for LEO happens to be fairly benign, and for GEO, it is in the tens of kilorats. Okay, so that's not something that is extraordinary. You can deal with this. And then we go to Mars, where you have lower temperatures to contend with. So these are negative 125 degrees centigrade, and then the upper temperature range is like 25 degrees centigrade. So there is a big swing there, and its integrated dose is about 5 kilorats per year. And yeah, this is not too bad either. But really extreme comes when you start to deal with Venus and the Jovian environment, for example. So Venus, it's the next bright object that you see in the sky after Moon, and it has a surface temperature of about 470 degrees centigrade, and its atmospheric pressure is about 97 times that of the Earth, and the atmosphere itself is supercritical carbon dioxide, so that's very, very corrosive. So it's an extremely hot environment for things to work, and whenever you have a landed mission on Venus, it is normally inside a protective vessel or a protective casing, which gradually starts to deteriorate as soon as it lands, and then the mission ends when the pressure vessel fails, right? So there is a limited time that defines the mission lifetime on the surface of Venus. Europa is a satellite of Jupiter, and Europa is very interesting because studies have shown that there's a thick layer of ice, and underneath the ice there is ocean. And there are speculations that when there is an ocean, there is a possibility of life being there, and people want to go search. On top of that, the surface of Europa is very dynamic because of the huge swings it experiences from the strong gravitational fields of Jupiter. So it's a very interesting satellite or a planetary body to study. But the problem is it's in the Jovian environment, which is extremely radiation intense. So you have a total integrated dose of 7 megarads or so in the range, and you can accumulate it in minutes to hours time frame. So your devices, especially electronic devices, have to be very radiation hard or very radiation tolerant. Radiation insensitive is actually preferred. So this is the extreme environment example. I'll connect this to why carbon nanotubes are useful. Next, we go to another motivation. So I show you a picture of 3 different rocks over there. So you just do the elemental analysis of these rocks using alpha particle X-ray spectroscopy. The graph looks like this. It basically has different elements here, and it has the abundances of the oxides on the y-axis. And if you notice, those are the 3 different rocks. The curves look pretty much the same, right? Do you agree? They are all sort of varying in the same way. So if you look at the elemental composition, you would think that all those 3 rocks are the same. But you have to do mineralogy or the crystal analysis of those rocks to find out that they really are very different classes. So when you do, for example, in this case, the Moss-Bauer spectra, you see that all 3 rocks are very different from each other. And it's a very important thing. So mineralogy is a very important analytical tool that you need when you go to explore planetary surfaces. And one of the gold standards for mineralogy is the X-ray diffraction. X-ray diffraction is used by multitude times and by many material scientists. And typically, laboratory scale X-ray diffraction, you have a goniometer, and you have a sample, powdered sample in the middle, and you have an X-ray source that just rotates with respect to the sample. And the theta that it creates, and the 2 theta is the angle at which you have the diffracted wave that comes out. And by notifying the pattern, by measuring or recording the pattern of the 2 theta, you can actually relate it to the crystal structure of the sample that is in the middle. Now, that is a pretty large laboratory scale instrument, and you need to miniaturize that. So David Blake at NASA Ames came up with a concept that has been very successfully implemented. In fact, it's one of the instruments that is flying on Curiosity. It's the first mineralogy instrument that is going to outer planet, non-Earth, extraterrestrial, that has an X-ray tube. And the X-ray tube, the way it works is instead of having a goniometer, he put a CCD screen in the back. And the X-ray is shined through a collimator onto a sample that is collected. For example, here in this case, it's on Mars. And the diffracted pattern is recorded on the photographic plate, CCD behind. And by analyzing the pattern, you can relate that to the X-ray diffraction spectra, and then you can understand what the sample is. The only caveat, or one of the requirements here, is that you have to make sure that the sample is well mixed, so you don't get statistical aberrations. So they have this is just a sketch schematic showing that, but it actually looks like a small, I would say, a coupon with Mars sample collected inside, that then is vibrated using a piezo, so that you're constantly mixing the sample, and you create the diffraction patterns. And if you use photodiodes, then you can also get X-ray fluorescence spectrum, and the X-ray fluorescence tells you the elemental composition. So you can do both in a way using this kind of an instrument. And this was implemented on Curiosity. So why CNTs? If you notice here, the X-ray tube, a standard way to produce an X-ray is you have an electron source, and you bombard a metal target using electron source, and you create a bremsstrahlung and characteristic lines of the target itself, which is in the X-ray range, and you use that as an X-ray tube. So you can miniaturize this X-ray tube. X-ray tube is one of the big components of an X-ray diffraction instrument, and miniaturizing this will automatically help you miniaturize these things. And for that, you could use CNTs. And another reason I forgot to tell you is, notice that there's a collimator here, which actually is used to bring a very narrow beam to hit the sample. So it is like you're basically casting a shadow. So narrower or smaller your focal spot is, sharper is your shadow of the image. Am I right? So that's pretty much what they're trying to do. So in order to achieve a very narrow focus, if you're already starting with a high intensity, very small source, it's easier to do that focusing, and CNTs will allow you to do that. Carbon nanotubes will allow you to do that. Secondly, most common electron emitters that have been used in the past for any of these instruments is a thermionic. So there are two ways to produce electrons. You either boil off the electrons out of the metal into the vacuum by giving it thermal energy, or you apply a field to a certain, I would say, structured sample, structured metal, and you basically you depress the band so that the electrons will tunnel out into the vacuum. So the second one is the field emission, which does not require a heater, and that's a very important thing for exploration, because now you don't have to worry or contend about having a heater that runs at 1200 degrees to 1400 degrees centigrade and deal with the thermal mass. So you have to manage thermal mass, and you have the heater power that you have to contend with, which can be in the order of watts, and that is an added mass, the actual mass itself. So you can eliminate that by using field emissions, and then it will give you a sharper focus, as I said. But there's another interesting use for this, and that is it's a low voltage operation. So by creating a lot of current, the X-rays are normally, they vary a square of the acceleration voltage that you apply between the target and the electron source. So you need a significant amount of X-ray flux to get a sufficient signal-to-noise ratio. And how do you achieve that? Is you either operate it at a very high acceleration voltage, like in the case of Curiosity, or the Chemin instrument that is on Curiosity, the operation voltage is around 28 kilovolts. That's quite high. There are the equipment there are instruments that are operated even higher than that, at 50 kilovolts. So those are pretty high voltage power supplies to use, and that they require special design, because you're miniaturizing everything. And when you're miniaturizing everything, you can imagine that a lot of the conducting parts are very close to each other. Like it could be the solder line, the clipped pin from a component, or the trace lines that are running on a PCB. They're all very close to each other. So if you have very close to each other electrical conductors, then you are familiar with what is called a Paschen curve, which is the spark potential curve. The y-axis shows you the spark potential, that is arcing potential, and the x-axis shows you product of pressure of different gases times the distance between neighboring electrodes. In this case, this is an idealized equation where you use infinitely parallel electrodes, where the field is uniform. But on an actual device, the field is not necessarily uniform. You have topology to it. You You have surface structures where there are higher field concentration locations and lower field concentration locations. So as a result, what happens here is the Mars atmosphere is about, Okay, so the Mars atmosphere is about 7 torr of carbon dioxide, and that falls right in this region. So which means you have to be very careful when you design your power supply to make sure that the trace lines are not extremely close, that you actually have an arcing event. In the case of 28 kilovolts power supply that is flying, we had to use a very exotic dielectric material, which is sulfur hexafluoride. And you can avoid that potentially if you're able to operate that equipment or that instrument at a lower acceleration voltage. And with the carbon nanotubes, you can operate them at 15 kilovolts, for example. And I'll show you the example of that. And how does the high current density help? Carbon nanotubes also, the design of architecture of nanotubes, they give you very high current densities, the kind of architecture that we have developed. And the high current density helps because you can make up for lower acceleration voltage by introducing by producing a lot of electrons, which will produce, in turn, higher flux of X-rays. And on Venus, it is especially important because on Mars, you can have a 10 hours of integration time to get the data. But on Venus, typically, you would expect the mission to last about 3 to 6 hours. So we always have a joke that, on a Venus-landed mission, we could introduce and we could end the mission in the same press briefing. So it can just happen in one shot. So it's a very limited time mission, which means you have to have a very fast data collection rate. As long as it is not detector limited, you can achieve that using carbon nanotubes, potentially. So the last motivation I had for you is the high frequency sources. So I told you that the terahertz region is very important for space exploration. So here is the electromagnetic spectrum going all the way from low wavelength to extremely high wavelengths right here. And here is your visible, little sliver of visible spectrum in relation. This is your terahertz, which is right below infrared and just above microwave. And this terahertz region is one of the least explored regions, and it's also a little hard to explore because of the absorption criterion of the things that surround us, especially water. But this is very important because 3 gigahertz to 3 terahertz, which corresponds to 1 millimeter to 100 micron wavelength range, there are a lot of emission spectra. So this is one of the old graphs that has been developed, or it's reported by Tom Phillips' paper, where it shows you the 300 gigahertz to 3 terahertz, that wavelength range corresponds to a black body temperature of 14 to 150 Kelvin. So here is a 30 Kelvin black body. Sorry, trying to find my mouse. Okay, there we go. So that's your 30K black body line, and here is your cosmic wave, 2.7K cosmic background line. And you've noticed that from 100 micron to 1 millimeter, in that range, you have tons of emission lines, molecular emission lines. So this is a very useful information if you're remotely trying to understand what is the composition of a remote space object is. And similarly, when you get the cumulative spectra, the energy output in the terahertz region from different galaxies with respect, and here's a graph that shows the same thing with respect to wavelength, older the galaxies get, more it shifts towards the red. So you can notice here that, for example, you can tell the age of this galaxy by saying that this one, the E galaxy, is actually a much younger galaxy than ARP 2020, I believe, 220. So these are all the techniques that they use in terahertz. But the problem is the signal that comes from in the terahertz region is very weak. So we often use heterodyning technique. So incoming space signal from the space is collected by an antenna, and then it is immediately heterodyne or enhanced using a local oscillator source that produces, I did it again. Okay, that produces the lines or the frequencies of interest that we are trying to enhance, and then it goes to a detector. And this local oscillator source is the issue. So when you make a local oscillator source, it's typically the ones that are used state-of-the-art is based on the nonlinear reactance change. It's just a frequency multiplier that uses a solid-state Schottky diode. And these are gallium arsenide diodes for high-speed operation or higher frequency, cutoff frequency operation. And you do multiple stages of frequency multiplication. For example, here, a typical, this is just an example for 1.2 terahertz source, where you start with a gun oscillator, which is about 100 gigahertz frequency and about 10 milliwatts, and that goes through a power amp, which increases the power by to 200 milliwatts, and then it goes through two doublers and a tripler to reach 1200 gigahertz. But notice what happens to the power. It goes down to 100 microwatts. So when you do multiple stages, your cumulative efficiency is about 0.05%, which is pretty bad. So you want to increase the power, the output power at these high frequencies. And one of the good ways to do that, and the difficult ways to do that, unfortunately, is to use or go back to vacuum tube days, where you had klystrons, backward wave oscillators, traveling wave tubes. So you basically use RF, the signal at the frequency that you want, and you amplify it by introducing an electron, energetic electron beam into it, and hence produce high powers. And that's one of the main reasons. And don't worry about the sketch. It just shows you a reflex klystron. This is an oscillator that works with the thermionic. And instead of thermionic, you can introduce a carbon nanotube field emission there. And then you have high power that is generating from at a high frequency. So one of the estimations that we did, a lot of the work going on in this area, obviously. So there's TWTs and backward wave oscillators being made, which require large magnets. But there are also klystrons being developed. This is a Stanford work, Klystrino, by Glenn Sheetram, who used micro-machined or electroplated permanent magnets. And the nanoklystron is the work that Peter and I did way back when we were trying to model or develop a reflex klystron for 1.2 terahertz that would basically fit at the tip of your finger, the whole klystron. So when you have such a source, as the frequency increases, the dimension of the device decreases proportionally, but the current requirements, also current density requirement increases. So you need a very high current density source. And you cannot use thermionic because if your entire device is about, about a millimeter by millimeter square, it's very hard to fit a thick thermionic source to it. So you are forced to work in the cold cathode regime or the field emission regime. So these are all typically the main motivations that started this work, and the applications are generating. But I'm going to go into the field emission itself a little bit, and then I'll move on to, I'll just show you briefly the X-ray tube example. But I think there's a more exciting example of digital vacuum electronics where you can make programmable logic gates using the vacuum technology that we have made, I'm going to show you, which operate at very high temperatures. So the field emission of electrons, in principle, as I mentioned, you tunnel the electron out by applying an external field. And you can do that pretty much from any surface, metallic surface or even non-metallic surface, if you just have a large enough power supply. You really need to have a pretty large power supply, but you can make it manageable by modifying the shape of the object that is emitting electrons. So, for example, if you make the object fairly sharp, then the radius of curvature will introduce a field enhancement locally at that tip. So the applied field, which is voltage divided by the gap between anode and cathode, gets amplified by a factor called field enhancement factor, gamma. So that gamma, if you can make it to the order of several thousands, then by just applying 1 or 2 volts, you'll be able to generate a lot of electrons. That's the principle. That's the idea. And typically, these field emission equations, they follow Fowler-Nordheim pattern. And here's the current, and that's the gamma. So notice that the emission current it varies as the square of the gamma, or the field enhancement factor. So it's a very important parameter. Phi is your work function, and here is your field, V by D, and that varies as square of the applied field. So you can enhance, or you can reduce the applied voltage by keeping anode-cathode gap really small, and then having a very high gamma emitters that you can shape them. And if you take natural logarithm of that equation, it converts itself into a y equal to mx plus c. And by plotting that, the slope of this y equal to mx plus c gives you a way to calculate gamma. So this is how whenever you get a field emission curve, you go back and you calculate gamma by assuming a certain work function for the emitter itself. So gamma is the key. There are many techniques that have been done in the past, and through simulation, when you have a single field emitter, you need a very good field penetration to make sure that it is emitting efficiently. And when you put multiple emitters together, this is a well-known problem that people use all the time in RF shielding, is that you have a electrostatic screening among the conductors. So your field penetration is not great, which means not all emitters will be emitting at the same time or at the same efficiency that you want them to. So even though a single carbon nanotube can give you 30 to 100 nanoamps of current, when you put them all together, it doesn't really produce as much. So in a large area, it's a big problem. So you really, gamma is a function of, or varies as the aspect ratio, and it's reciprocal to the CNT number density, which is basically relates to your electrostatic screening effect. And there are multiple work that has been done by different groups, and a group led by Nilsson said that you need it's really an optimization problem. How do you bring so many emitters together so that you have a good combination of number density and as well as a low electrostatic screening? And that is done by different ways. So one of the ways that was identified is if you keep the distance between two consecutive emitters to be twice the height of the emitter itself, then you actually can get a pretty good optimum density and reduce the field electrostatic screening. But experimentally, there have been groups that have shown that it really needs to be 1-to-1 ratio. So there is a range of opinions and proven results. So in order for us to develop a high current density field emitter, we ended up doing a bundle architecture, which I'll show you next. One of the reasons why we wanted to do this is because when you do the miniature instruments, you need them to operate in vacuums, and these vacuums are miniature cavities. So in those cavities, if you've done any micro machining or made micro cavities, you know that it's very difficult to achieve extremely good vacuum in a small volume. So you need these field emitters to operate very well in the small volume. So that's one of the reasons why CNTs work well, because there is a natural redundancy of multiple emitters being there. So what we ended up making was, after sufficient experimentation, an architecture like this, which looks like each of that is a bundle of carbon nanotubes, which is about 2 micron or 1 micron in diameter, and they are patterned so that the edge-to-edge distance is about 5 microns. And then you grow them to a few tens of microns to 100 microns tall, and you try different combination of these on the same sample. So you just change the diameter and the array distance. And that's what this graph shows here. And when you scan a microprobe across for the same potential, you will notice that at one particular number, the current emission is almost an order of magnitude higher than anywhere else. And that turns out to be this combination. It's between 1 and 2 microns diameter field emission bundles, which are spaced about 5 microns from each other. And that they produce quite high. About 2 to 10 amps per square centimeter routinely is what we get for very low applied fields at 4 to 8 volts per micron, which means if you make a device that's only about a micron away, the anode to cathode, then you can pretty much get you can apply digital voltages less than 5 volts and achieve the kind of current densities that you want. So it's a repeatable high current density you can achieve, and these are some of the results that we did in comparison to then produced results by different groups. And here are our results. You want more right, upper right you go, the better it is. And one of the things we did was we wanted to see how it's actually working. Why is it working? Because we really don't know why the array works. We know that empirically the array works, but we clearly don't know why the array works. And we worked with Motorola Research Lab. At that time, they had a flat panel display division. And Ken Dean, a good friend of mine, and Lindy Tissinger and Scott Johnson, we worked with them because they had a mechanism to observe field emission in real time. So they have a scanning electron microscope where you put the sample in, and then your observation beam is coming down onto the sample, as shown here. So here is this shows you the nanotubes which are perpendicular to that axis, and the microprobe anode which just runs through. So that's the SEM of the same thing. So it's the microprobe and then the CNT bundles. And when you apply a field up to a certain current, you can observe it, because beyond 10 to 15 nanometers, the emission current starts to interfere with the observation electron beam, so you won't be able to get the image well. But if you do that, I apologize because you won't be able to see it very well here, but when you apply field, you can see that the nanotubes start to straighten up. They stand up and then they rearrange themselves under the applied electric field, because you have the charging happening at the top. So that's one of the reasons why we think that a optimum extremely high current density emission is happening from these. And they also fail because these nanotubes are not very firmly adhered to the surface. So we ended up making large area samples, which are 100 microns in diameter. So here's the footprint. It's about 100 microns, and they're all 1 to 2 microns diameter bundles, spaghetti kind, and spaced 5 micron apart. And they consistently produced very high current densities. So these are all at the 10 to 15 amps per square centimeter, each one of them. And look at the sharpness of the knee of this curve itself. And this is the normalized voltage. So they're all in the 2 to 6 or 2 to 8 volts per micron. The reason for two of these groupings here is these samples contained very high gammas, the tubes with very high gamma, more than 7,000. And on this side are the ones which had amplification factor of about 4,000. So that they clearly distinguish to tell you how important having a very high field enhancement factor is. So we use this, and then it's good to have very high current densities, but you need to sustain them over a period of time, because it's not enough to measure them for a few minutes and then turn it off, you're done with it, you publish a paper and everything is good. But when you want to use it, it needs to happen, or it needs to work for thousands of hours. And you do a lifetime test, unless you do certain modifications to the sample, you won't be able to use them, because there are two ways in which these field emitters fail. One is they have a gradual decay. They have a gradual decay that happens because of the tips burning slowly while under field influence, and also the sputtering of the anode material that falls on the field emitters and masking the tips that are emitting. So you have an issue of constant decay. But another interesting issue is right here. So in this part, it tells you that this is the voltage curve. It's maintained constantly in this region, and this is the current curve. If you notice, even though the voltage is constant, the current is slowly increasing. And the reason why this happens is nanotubes are not very firmly adhered to the surface. So they're about, addition strength, if you measure without doing any surface modification, it tends to be in the range of a few tenths of kilopascals. So it's very easy to draw them out when you are applying a field of 8 to 10 volts per micron. Okay, so when you apply such a force, you're slowly pulling the nanotube up, but the nanotube is not completely removed from the surface because it is held down by the surrounding nanotubes. So you're constantly increasing the nanotube's distance, and it keeps moving up. As a result, the gap keeps decreasing. When the gap keeps decreasing for the same applied voltage, your field starts to increase because it is V by D. And as a result, the current starts to go up to a point where it leaves the rest of the nanotubes or the cathode surface, and then just goes and attaches itself to the anode, and at which time a catastrophic failure happens. And that's the reason why you see a step drop in current here. And that can be seen in a more, this just is an EDX that shows you that we do see that when you apply, when you use these anodes like copper and glassy carbon, you do have a sputtered material that falls on the emitter itself and masks the surface. And it's the same thing here. So you can see that the circular region of the emitter surface is completely discolored, and it's roughened out. And that's one of the reasons why you have a gradual failure. But here is the catastrophic failure. I always enjoyed this experiment. You have a constant voltage, and then at some point it starts to increase, and then you have a drop in the current. And that's because that's the beginning, and that's at the end, when you have nothing left or nothing left underneath the probe itself. It's all removed and dislodged from the substrate and pulled up. So these things have to be developed or studied well, and we have ways now to do that in terms of surface modification to increase the adhesion, so you can have a long life and pulse mode operation to enhance the lifetime of the source itself. So I'm going to quickly go to the first application, which is a miniature X-ray tube, and I'll just show you. I talked about this already, the Bremsstrahlung with the characteristic lines, and it's a standard way to produce. You have a cathode, and then you shine electrons at a certain acceleration voltage against a shaped target, and then you produce X-rays in the perpendicular direction. And you can use either thermionic or carbon nanotube. And we used carbon nanotube, and here is the example. So this is a nanotube-based X-ray tube. This is a very small X-ray tube. It's only about 5 centimeters long, about 2 inches, and 1 centimeter in diameter. And it uses copper and cobalt. And as I mentioned, it operates at a low acceleration voltage, 15 to 20 kilovolts. And we have a certain current that is emitted, and then you produce about 10 to the power of 5 photons per second, which is a reasonable photon flux for measurement purposes. And we calculate the efficiency of emission here, which is actually the current that reaches the anode versus that is actually produced at the cathode. And for different percentages, you can notice that this is an X-ray production gas. These are the characteristic lines for cobalt, and that's K alpha, which is 6.92 kilo electron volt, and that's K beta, which is 7.69 kilo electron volt, and you have a pretty high flux at K alpha, which is about 6,500 photons per second per square millimeter. That is going through a collimator of 200 microns in diameter. And the same thing for copper. Is at a slightly higher efficiency, and applied voltage is about 16.5 kilovolts. And you see the copper K edge, which is about 8 kilovolts, and K beta, which is about 8.9 kilovolts. And you have a sufficient photon flux that is coming off. And this is an unoptimized source. So when you optimize it, you expect it to work better. So let me move on to the next topic, which is the digital vacuum electronics. So this is one of the recent developments that we have made. And I mentioned to you that there is a big need for high temperature electronics for computational purposes and control purposes. And that need actually opens up from 350 degrees to 700 degrees centigrade. There's a lot of work done in lower than that. But in that region, the work is still ongoing. And there are different techniques that is used. For example, state-of-the-art, Honeywell is one of the companies which does a lot of this work using SOI CMOS and silicon carbide-based devices. These are solid-state devices. And they've been, and NASA Glenn has a pretty extensive program in this. And they do 500 degrees centigrade. They've demonstrated several things up to 500 degrees centigrade. But the thing is, the integration level of these components is fairly low. They're mostly in discrete components. So you take them and you put them on a printed circuit board, and then you use them. They don't really come as a full microprocessor, for example, like the way the silicon technology is. So you start with discrete components, and then they've shown, past literature has shown, you can operate them at 500 degrees centigrade and tens of megarads of radiation. But there are also NEMS components. These are non-electromechanical systems. These are basically silicon carbide wires. So they're switches that just move between two poles. And those can be radiation hard or even radiation insensitive if you choose to. And they've been operated up to 600 degrees centigrade by Case Western, Mehran Meragani's group. And we have been working in using our field emission sources, what is called digital vacuum electronics, which has been shown to operate at 700 degrees centigrade. So what we're trying to do is we're going back to the vacuum tube days from the transistor days, because we feel that we now have a technology that can produce the device density that is comparable to that of solid state. So, and why vacuum electronics? In this case, the electron transport takes place not in material, but rather in vacuum. So it naturally, inherently radiation insensitive, and it can be high temperature tolerant. Many of the vacuum tubes in the past operated at 1200 to 1400 degrees centigrade. So, how does it work? This is the field emission curve that I showed you earlier in the sketch. So ETH is the threshold field, and that's is any arbitrary field that you operate this device at. And you can notice that there's an exponential increase in current. So to go from nanoamp to microamp range, you actually have a 0 to 1 state that you can define. So this is a sketch that shows you a CNT emitter, single emitter on an anode, which is separated by a distance d. And you apply a voltage V, or the field E, which is V divided by D, then you can create a graph like that if you're pulsing it especially. So you increase the applied field from threshold to E, and you have a corresponding current at the anode, right? Now we can make it one level complicated. So this is the same thing as I showed you earlier. Now we're going to add a gate to it, a gate electrode surrounding it. So now you have a source, or cathode, gate, and then drain, or the anode. So now what happens is, if you do not have any voltage applied to the gate, or no field on gate, your current goes straightly to the anode, because you still have a applied voltage V, and the distance from anode to cathode is still D. But what happens is the gate plane is actually it's closer to the cathode than the anode. So the distance from cathode to the gate is less than D, which means if you apply the same voltage at gate, your essential field from the gate is higher than the anode. Do you get that? Okay. So what this allows you to do is when you apply the gate voltage same as the anode, if the cathode level is below the gate plane, then the current just goes into gate rather than the anode. So you have no current at the anode by just turning on the gate bias. So you create, if you take anode current and you put a pull-up resistor, I'll just show you that. You put a pull-up resistor here, and then you can draw the voltage state out. So if you have a non-zero anode current, then you have a voltage state to be 1. And if you have a zero anode current, you have voltage state to be 0, right? So using this, there's a interesting geometry here was created, which uses 3 different gates, okay? So it has a 3-gate input and 1 anode and 1 cathode. And you bias these gates so that you can actually create a universal programmable gate. And how does it work? It is shown in this cartoon here. So you have 3 gates, G1, G2, G3, and these are cathodes that are in between gates. And whenever they're green, assume that they're emitting. That's the convention that is used. And when they're black, they're not emitting to the anode. And when you bias them, when you turn the bias on, the gate becomes red in color. So you have here, when you turn the anode current on, all the cathode is emitting to the anode, so you have non-zero current. And you turn any one of those gates on, you still will have one of the nanotube emitters emitting to the cathode, to the anode. So you have a non-zero current. But you turn any 2 of the gates on, then you end up turning off all of the cathodes from emitting to the anode. So your logic state becomes 0. Same with 3. So if you take this and put a truth table together for a 3-input gate, this, if you go back and verify, it looks like a NAND and a NOR. It's a combination of 2 gates together. So using this, you can actually create adder circuits, full adders, half adders, and other logic gate-based computational circuits. And the advantage is, because it is vacuum, you can operate it at very high temperatures. And you can make the line widths very, very small so that you can reduce the Miller capacitance, that is the capacitance that is between the gate and the anode and the cathode. You can reduce that to femto and attofarads. So your switching speeds can be as high as or comparable to those of solid-state devices. So, and that's shown here. For example, if you take a full adder in a solid state and you use a 190 nanometer line process, the footprint, it takes about 32 transistors to make a full adder, that the footprint tends to be about 14 microns by 5.5 microns. And the same thing, if you use IMG is the inverse majority gate that is using the digital vacuum electronics I mentioned, you use a 0.5 micron line width for the gate, then your footprint area is comparable to that. So it's 18 by 4 microns. And that sort of gives you an indication that you can actually create a high density device. The only catch is you have to vacuum package them. That's a different problem. So here's the first device that we made. It's a very unoptimized device. This was a proof of concept device that we made. And the line width here is about 20 microns. So it's a huge capacitance. So you don't expect them to switch at nanoseconds at all. And we have multiple bundles of nanotubes that are integrated in here. So one of the interesting things that we do in the group is make the devices from the nanotube or use nanotechnology with microtechnology and build the interfaces. So we construct devices that use both. So they actually become usable components in the end. So the CNTs are integrated here with silicon micromachined structures, the gate structures. And that's the test circuit. We just bias them. And for high temperatures, you need special packaging because things melt at 700 degrees centigrade, as we found out. And we use a Makeover chip this was made in-house. We use gap welding to hold the wires together, and then you hold the device together, up in place, and a silicon micromachine anode that was put on top. So as you can see, none of these structure is very conducive for high frequency switching, but it'll do DC switching just fine. So after doing this, we put it inside a tantalum tungsten heater coil, okay? And then we heated it to 715 degrees centigrade, and that's the device right there on your on the ceramic mount that was made, and we switched at this temperature the logic states, And the applied voltage at the anode is 50 volts. That's because that's defined by the gap. We had a larger gap in this device. And these are the 3 gate voltages, which toggled from 0 to 10. And the threshold current was always about a nanoamp. So anything below nanoamp, it was a noise. So it's registered as 0. And above a nanoamp, it is registered as non-zero current, which is 1. So by using that, you can produce the same truth table that I earlier mentioned. So this is the DC switching operation. So this is one of the first devices that has been demonstrated in the digital vacuum electronics. And the work is going on, but one of the quick things that come to mind is, what about the current contribution? Is it only from field emission? Because you're heating the electron emitter, so you could as well be having thermionic. If it is thermionic, then what is the level of thermionic? That can be deduced from the thermionic equation. If you go back and plot for the kind of temperatures that we were working at, the 700 degrees centigrade, the current is in the picoamps, which is very negligible. So it's hardly registered. I'm sorry, that's femtoamps. So that's in the noise. So I don't think it's a thermionic. So that much we are very sure. And using field emission, then we can actually make these devices to operate much further. And the frequency operation relationship, we can go back and we can look at this by optimizing the transconductance of the device, etc. But the bottom line I wanted to tell you here is, if you can control the space charge that is at the anode, which will slow the operation of your device, then simplistically speaking, the maximum frequency of operation is only limited by the transit time of the electron from the cathode to anode. So however fast it goes, that's pretty much how fast the device will work, theoretically speaking. And it turns to be about 200 gigahertz or so in terms of speed. So that's comparable to solid-state devices. But I wanted to show you this because this was I just thought it's funny. It's anticlimactic when you go from 200 gigahertz to this, where we had this huge unoptimized device and long cables measuring the frequency switching, and our frequency of switching was about half a hertz, or at best. That's because of the parasitic capacitance that was introduced in the device and the cable itself. So obviously there's a long way to go there in terms of making the device switch at very high frequencies. There are lots of issues to be addressed in terms of how well you grow these tubes. Tubes tend to grow. You should have a very good, well optimized process to keep the growth of the tubes confined to a small location. Otherwise, they grow tall, and then they can short with the neighboring electrodes. And you could have a dislodging of the CNT bundles, as I mentioned earlier, if you're not careful with your applied field. And there's a significant morphology that is forming because of the gate formation on the silicon structure. So when you do multi-layer process, it's difficult to keep the line widths well defined. So, and then vacuum packaging, of course, is an important issue that we are working on. We use solder reflow bonding. I can talk to you if you're interested at a later time. But in summary, I know all of you are tired, I can see. So this is the exciting slide for you. So in summary, high-performance CNT field emitters have been developed, and a lot of different groups have done different ways of making them. And we are using an array of bundles that we are using for both miniature analytical instruments and digital vacuum electronics and those kind of applications. We are targeting specific space applications to take the technology forward. And I've shown you the operation of a first-of-its-kind device that uses digital vacuum electronics, which is a programmable logic gate that uses vacuum technology. And I also mentioned to you about the issues that you need to face in terms of when you're integrating nano and micro structures together, and the improvements that have to be made for these devices in order to make them work in a long term in an application. So that's pretty much all I had. Thank you for your attention. Good time?
Take questions from the audience.
Yes, sir. Are these single wall tubes? No, the question is, are these single wall tubes? Most of the field emission tubes that we work on are multi-wall. They're typically about 20 nanometers in diameter. Single wall tubes can be used, but because we want them to be vertically aligned, single wall tubes are a little difficult to do that unless you do large numbers which are highly dense. So, any other questions?
I have a question. Are there any terrestrial applications for things at this is the first time I saw an image of something operating at 700 degrees Celsius.
Actually, there is. The project was started by DARPA. There is a need in defense for things that operate at 700 degrees centigrade. And a lot of the work in 700 degrees centigrade has been done, even the NEMS work that I mentioned, for the DARPA projects. So there is a terrestrial application. Obviously, I don't know or I can't tell you what it is. But there is, yes.
Other questions? Yeah, John has one.
What limits the pressure that it can operate at?
I'm sorry, could you repeat that?
What are the limits on the pressure that it can operate for example, the X-ray, the field emission for the X-ray device? Is that mean free path for the electrons or something? Or?
You mean the inside the vacuum envelope?
Yeah.
Oh, the pressure typically that it operates is about 10 to the minus 5 to 10 to the minus 6 star for the nanotube devices. If you can also have other cold cathodes, the ones that are done in the past, which use metal tips and silicon tips that are coated with metal. Those tend to erode because of the sputtering effect. So those require very ultra clean, like they need to be at 10 to the minus 8, 10 to the minus 9 torr. But they're also developing a lot of coatings that can protect them to operate at a much dirtier vacuums. But I just don't know of any device that is operating right now, other than nanotube ones.
You mentioned that it's difficult to have a good vacuum in a small device. I don't know what the issues are there. Could you?
It's just a surface to volume ratio.
Okay.
Yeah. So and also when you have nanotubes, all those bundles, the majority of that is air pocket. So you can have virtual leaks that will be very hard to clean. We have actually made a vacuum package using solder reflow bonding at a chip scale. And if you bake the package well enough at a higher temperature to remove all the adsorbates, then you can operate them for a fairly long time. Even after 6 years, we had one of the diodes operating quite well. It's mostly the issue is as the device ages, we don't know exactly. We have not done studies to see what's happening to the emitter inside. In principle, nothing should happen because they're all enclosed, but who knows?
Other questions? If not, let's thank the speaker again.
Thank you very much.
You can always come down and ask him if you have any NASA questions, NASA graduate fellowship questions, and things like that. So. Yeah.